Hi everyone, welcome to my presentation. Today I want to share a story about how I found 16 Microsoft Office Excel vulnerabilities in 6 months. I'm Quan Jin. Let me first introduce myself. I am a security research expert from DBAPP Security Liaoying Lab. I previously worked at Qihoo 360 Advanced Threat Analysis Team. I once spoke at Blue Hat Shanghai 2019 conference. I mainly focused on vulnerability research and in the wild zero-day hunting. I have gained more than 25 CV acknowledgements from Microsoft and Adobe, and I was ranked as top 39 in the 2020 MSRC Most Valuable Security Research list. I, with my team, have captured several in the wild 0 days on Windows platform in the past 3 years, including Office, IE, Flash, and Windows kernel. The most recently in the wild 0 day we hunted is CVE 2021 1732. This is a Win32k privilege escalation vulnerabilities which affects Windows 10 18.3 to Windows 10 20.2. This is the agenda of my presentation. I basically will tell my story in this order. At the beginning of 2020, I decided to learn something about fuzzing. I first read some papers about fuzz, including finding security vulnerabilities with modern fuzzing technologies. After learning the basic concepts about fuzzing, I decided to do some fuzzing job on Windows platform. My goal was to get a CVE number from Microsoft through fuzzing. There are many fuzzer tools for Linux platform, such as AFL, Lightfuzzer, and Hungerfuzz, but there are less fuzz tools on Windows platform. WinAFL is a great tool. However, it cannot handle large and complex software such as Microsoft Office. Over the past 3 years, hundreds of bugs on Windows platform were found by WinAFL, which means there are basically no chance to find more bugs through it. Some researchers make some improvements on WinAFL and find more bugs based on their custom WinAFL. From my perspective, I want to choose a target which is less targeted by WinAFL, and I am familiar with this target. There are several candidates: Adobe Reader, Internet Explorer, and Microsoft Office. Let's review them one by one. Adobe Reader was heavily fuzzed by WinAFL at the year of 2018. Internet Explorer was heavily fuzzed by Tomato during 2017, 2018, and 2019. Few people have done effective Office fuzzing work, but there do have some, such as Jacques Kapper's presentation and POC 2018. It seems that Microsoft Office is a good candidate for me, but there comes 2 questions. Number 1, is it possible to find a bug in Microsoft Office on several months for a newcomer in fuzzing? Number 2, Microsoft Office consists of multiple components. Should I choose Word, PowerPoint, Excel, or other component to fuzz? Let me first answer the first question. I am a newcomer in fuzzing, but I have extensive experience in Office vulnerability analysis, so it's possible for me to find a bug in Microsoft Office. To answer the second question, I counted the Microsoft Office CVE numbers and their distribution from 2017 to 2020. The initial statistical time is up to April 2020, and I updated the statistical data in June 2020. Here is the up to June 2020 statistical results. Note, the column office represents office vulnerabilities that do not specific components, which means that they may be Word, PowerPoint, Excel, Outlook, or other vulnerabilities. We can learn something from the above table. Number 1. Around 2018, Microsoft made a change to the disclosure number of Office vulnerabilities to make the classification more detailed. Number 2. From 2017 to 2020, the Excel components has the most vulnerabilities almost every year. Number 3. From 2017 to 2020, the PowerPoint component has the least vulnerabilities almost every year. If a security researcher invests the same amount of time in security testing for each Office component, Excel is obviously the most hopeful one, and PowerPoint is the least. Word and Outlook are in the middle. If I can choose only one target, it will be Excel. So, let's find Excel. Now I have selected Excel as my target. Before starting fuzzing, I need to evaluate the feasibility of the basic steps involved in Excel fuzz. A common fuzzing process usually includes the following stages. Seed. How to collect seeds. Mutator. How to mutate. Detection. How to catch exceptions. Triage. How to classify and deduplicate crash files. Reproducer. How to reproduce the crash. Report. How to report the vulnerability to the vendor. Let's examine them one by one. Before fuzzing Excel, I need to collect some Excel files as seeds. After counting the file types involved in the Excel vulnerabilities announced by ZDI in the last 3 years, I realized that the proportion of vulnerabilities in the Open XML format is far less than that of the OLE2 format. So I began to focus on XLS files. After some exploration, the source of my seeds is as follows. Here. Many fuzz tutorials tell us that the more files are not the better, none the bigger the better. So I need to minimize the collected Excel files. If the fuzz tool is WinFL, you can use the built-in components to distill the seed files. I don't want to use WinFL, so I need to implement this function by myself. While trying to solve the above problem, I saw 2 blogs by Jacques Kapper. Unfortunately, at the time of writing this presentation, these blogs are no longer accessible, but I read these 2 articles in detail at that time. Although it is no longer possible to obtain relevant knowledge from the author's blog, Jacques Kapper once shared his experience at the POC 2018 conference. However, the ideas of corups distillation are similar between different tools. For the software you want to fuzz, first select a model, then use the tools as initial seeds to make statisticals on the model coverage. The goal of this is to select the smallest number of files with the highest model coverage and hope that these files are as small as possible. With the help of static count and dynamic execution, I distilled a set of Excel seeds in an acceptable time as the initial seed for my fuzzing. Mutation algorithm is an important part of fuzz, and its quality directly affects the result of fuzz. I transplant the following mutation algorithms in Hunger fuzz, including bits, increase byte, decrease byte, negative byte, bytes replace, ASCII number, clone bytes, AD, and sub. For the remaining mutation methods in Hunger fuzz, after carefully evaluation, I choose not to transplant. I also integrate all the values of the byte replacement part of AFL, light fuzzer, and Hunger fuzz, and constructed a mutation value replacement table covering these three fuzzers. The detection part can be simply abstracted into automatic start of the program, open the file, monitor process, and catch the exception. There are many good solutions on GitHub, which are generally implemented by WinAppDbg or PyDbg. Vulnerabilities by Jacobs is a good example. In order to improve the catch rate of heap memory access exceptions, I use global flags to enable page heap for Excel process. During the fuzzing process, hundreds of crash files will be collected. How to effectively classify them is a science. Based on the existing experience, I mainly pay attention to the following conditions. Number 1. Access valuation. The exception code is 0xC605. Microsoft doesn't accept state exhaustion vulnerabilities such as 0xC50FD. Number 2. Non-zero pointer reference exception. Microsoft doesn't accept non-pointer reference vulnerabilities. Based on the above considerations, my classification ruler is to distinguish a non-pointer reference from a not non-pointer reference, distinguish access valuation from other exception types. Under this ruler, those not non-pointer with an exception code of 0xC6005 are the crashes that I need to focus on. My classification ruler for Microsoft Office Excel exception is as follows. Non-pointer reference, including read access valuation and write access valuation. Read access valuation include out-of-bound read and use after free read. Write access valuation include out-of-bound write and use after free write. In terms of real-time synchronization of the fuzz results across multiple virtual machines, I use a FTP server which serves in a virtual machine as the result server, and install the PyFTP Live model in server and client. Not all crash files can be reproduced, so I write a reproducer based on my fuzzer. This reproducer is used to reproduce the crash results in various full-patch Office environments and record the reproduced results. I make multiple Office environments to reproduce the crash files, including but not limited to these: Office 2007, Office 2010, Office 2013, Office 2016, and Office 2019. Each version I make a no-patch environment and a full-patch environment. For those reproduced by the reproducer, I will perform some manual check. If both passed, these files are regarded as valid vulnerability files. When a crash file is successfully reproduced, it can be automatically generated a professional report with help of bug ID. It should be noted that bug ID can only run on Windows 10, so a Windows 10 plus Office environment with the latest Office and full patch version need to be made. Below is the bug ID report I generate from one of my Excel vulnerabilities. Once you have the bug ID report, you can submit the vulnerabilities to MSRC. MSRC research protocol is as follows. The specific format of the vulnerabilities report can be referred to here. The prod and bug ID reports can be uploaded as attachments. My entire fuzz machine is only one computer with the following configuration: i7 8700 12 cores, 16G DDR3 RAM, 3.G primary preference, 1T HDD. In addition, I also have a laptop for reproduction and report generation. These are all my fuzzing equipment. Throughout the process, I encountered at least the following problems: dialog click, virtual machine size, speed of execution, version switching, fuzz strategy, crash management. Let's see them one by one. The Excel software has various dialog boxes during the executing process. Some dialog boxes, such as Safe Mode, can be resolved by cleaning the registry, while others need to be manually clicked. My way of solving these dialog boxes are as follows. Number 1. Before each start of the file or the end of the file, clean up the relevant registry item. Number 2. Add a simple simulation click tool during the fuzzing, such as starting a separate thread for window enumeration and dialog click. A good example is Cuckoo Sandbox Human plugin. These methods can only handle most of the dialog box click problems. There are still some dialog boxes that I cannot solve. But there is no need to be perfect. It is enough to do this. I use VMworld to fuzz. During the fuzzing process, a large number of files are generated in each virtual machine. These files will gradually increase the size of each virtual machine. Over time, the disk overhead of the host will increase significantly, usually several to dozens of GBs per virtual machine. In order to solve these problems, you must ensure that current fuzzer has effectively cleaned up the files generated by the previous fuzz before starting the next file, mainly the following folders. Otherwise, once the number of fuzz executions increases, the size of the virtual machine will explode. As a result, the fuzzer will stop. In addition to above operations, I also DISM tool to regularly clean up the temp file inside each virtual machine and configure the virtual machine to automatically clean up the disk after shutting down. In this way, the size of each virtual machine will be automatically reduced after shutdown, and the size of each virtual machine can be restored to the original size at a fixed interval, such as few weeks, thus creating a basis for For continuous fuzzing, speed of execution. When other conditions remain unchanged, the speed of fuzzing directly affects the output efficiency. After some testing and evaluation, I think the main factors affecting Excel fuzz are as follows: file size, office version, the stability of fuzzer, disk I/O, CPU cores, RAM, and primary frequency. File size. In the corups distillation stage, I have selected as small a seed as possible when ensuring coverage. From a statistical point of view, for Excel, files smaller than 400 KB are more likely to produce vulnerabilities. There are many versions of Office. The higher the version, the slower the opening speed. From another perspective, the higher the version, the larger the amount of code and the number of potential vulnerabilities. I need to make some trade-offs. After a period of evaluation, I decide to focus on vulnerabilities, which exist from Office 2007 to Office 2019. After making this choice, I can speed up fuzzing by choosing to execute the file in a lower Office version. Although Office 2007 and Office 2010 have successfully withdrawn from the support list, they are useful if the crash file which collected in these environments can affect the latest version of Office software. The main fuzz environment I finally chose is Office 2010. After many fine-tuning, my fuzzer can be stabilized on 10 virtual machines, and each virtual machine executes an average of 15,000 files per day, that is, run about 150 files per day. The stability of fuzzer. If a fuzzer is unstable and crashes itself when executing, that is sad. Some fuzzers that use WinAppDBG may have this problem on x64 environments, so I mainly run my fuzzer on x86 environments. After observing an improvements for a long period of time, my fuzzer has achieved relatively good stability. It can run for weeks without problems. This problem was discovered through observation. My fuzzing environment uses HDD. When using VMworld to open multiple virtual machines, I open up to 11 virtual machines on a single computer. Disk I/O will become very stuck. Due to the limitation of disk I/O, the fuzz of inner virtual machines will cause VMworld itself to hang on for a long time, which significantly affects the fuzz speed. Sometimes the fuzz in a single virtual machine ends abnormally. It is necessary to clean up the environment in the virtual machine and restart the fuzzing, or restart the relative virtual machine to resume the fuzzing. This process is a waste of time, so I think SSD will improve a lot. The number of CPU cores and the RAM capacity directly determine the maximum number of virtual machines that can be opened at the same time. Bigger the two indicators, the better. The primary frequency directly affects the open speed of the program. The bigger the primary frequency, the better. During the fuzzing, It is necessary to consider the inconsistencies of processing the same file by different architectures, x86 and x64, different patches, no patch and full patch, and different language versions, Chinese and English. I mainly consider the following things. Files that cannot be triggered on x86 can be triggered under x64. Files that cannot be triggered in a lower patch environment can be triggered in a higher patch environment. Files that cannot be triggered in the English environment can be triggered in the Chinese environment. Therefore, I test the above things with each set of these files and gain some actual crashes. Fuzzing strategy. I think this part is the most important of my Excel fuzzing. What I have is a machine consists of this. What I want are obtain as much vulnerabilities as possible in the shortest time. Finding vulnerabilities that exist in all versions of Office. This forced me to do many thoughts and explorations on how to configure fuzzing strategies. My experience on fuzz strategies, including but not limited to the following. Skip the first 512 bytes of the header of the OLE2 files during mutation to improve the effectiveness of mutation. Using older version of Office for fuzzing to improve the speed of fuzzing. Use smaller Excel files for fuzzing to increase the speed of fuzzing. Use Google to collect XLS files which were made with old versions of Excel in the 1990s and 2000s and added them to the initial seed collection. Select Office attack surface that may cause problems based on my experience, for example, pivot table, and then select the relative files for fuzzing. For a period of time, select the Excel files that is most likely to cause problems in the current result and increase the proportions of them, because the file that cause a problem often cause other similar problems. For the same files, only use one mutation algorithm for fuzzing within a period of time, and continue to observation the effectiveness of the current mutation algorithm. If there are still more new output after a week, continue to fuzz. If there are almost no new outputs after a week, switch to another mutation algorithm. Categorize the size of seed file, such as 0 to 100 KB, 101 to 400 KB, 401 to 1 MB, and larger than 1 MB, and test each seed set of a specific size in a specific period of time. The same file will be tested in full patch and no patch environments, in Chinese and English environments, and in x86 and x64 environments. As more and more results are obtained from fuzzing, how to manage these crash files has become a very important thing. I mainly consider the following conditions. How to merge the same cases generated in different fuzz machines. How to exclude crash cases that have appeared before the newly added crash files. Regarding how to merge the same cases generated in different fuzz machines, I have explained in the section Methodology Implement Change above. I use a FTP server to receive crash files across virtual machines. If a crash file has the same model and the same crash address with a previous file, the server will reject it. Every once in a while, I will drop out all the crash files in the FTP server and reproduce them in a full-patch environment with the help of my reproducer. I make several full-patch environments, but only one is frequently used. Only those newly appeared crash files need to be examined. Therefore, I use a Python script to save all crash files produced by the reproducer to a local database. This database is just a simple folder list, but it is very effective. When the number of crash cases in the database becomes more and more, the newly appeared crash files will be fewer and fewer. At the same time, the vulnerability rate of these new files will be higher and higher. After half a year of fuzzing, I reported a total of 20 Excel vulnerabilities to Microsoft. 2 of them were marked as valid but will not be fixed immediately. 1 was marked as won't fix. The remaining 17 vulnerabilities are all fixed and help me receive 16 CV acknowledgements from Microsoft. 1 of them is duplicate. This table is a summary of my fuzz results. Note: O here refers to Office 2010, Office 2013, Office 2016, and Office 2019. And case 61461 has been fixed in the January 2021 patch day, but it is duplicate. I have not tracked down its corresponding CV number. Below I show some cases found by my father. CV 2020-1494 is an unallocated memory write issue in Excel process. We can say it crashed at memory move function. This vulnerability affects from Office 2010 to Office 2019. CV 2020-17126 is an out-of-bound read issue in Excel process. We can say it is also crashed at memory move. This vulnerability affects from Office 2010 to Office 2019. Let's see the third one. CV 2020-17127 is an use-after-free read issue in Excel process. It is a nice UF. We can say it tries to read a virtual function table from ECX and saved it to EAX, and it tried to read a function address from EAX plus 8 and call this address. So I think it is a nice UF. Unfortunately, this vulnerability only affects Office 2010, but I still think it's a nice UF. For now, my fuzz method has the following shortcomings. As mentioned earlier, in order to improve the speed and efficiency of fuzzing, I selectively ignored some potential vulnerabilities in terms of strategy, such as vulnerabilities only in the newer Office version. The fuzz method in this presentation is aimed at the vulnerabilities that affect all Office versions. Due to the limitations of my testing methodology, those vulnerabilities that only exist in the latest version of Office, but not in the lower version of Office, cannot be found through my fuzzing method. If the current disk can be replaced with SSD, the file read-write speed will be significantly increased, which can improve the fuzzing speed a lot. The mutation algorithm can still be improved according to observations. After translating the Hunger fuzz mutation algorithm to my custom fuzzer, the fuzz output has increased significantly, which shows that an effective mutation algorithm can greatly improve the fuzz output. If I continue adding better mutation algorithm to the current fuzz framework, it can further improve the results. The start and stop time of Excel process is too expensive. If there is a better way for simulating Excel execute process, it will significantly reduce the opening and closing time of the Excel process, and the fuzz speed can be greatly improved. The corups distillation method in this presentation uses static code coverage statistics. Compared with dynamic coverage statistics, this statistical method has lower coverage accuracy. Only a rough coverage assessment can be done, so there is room for improvement. The initial seed set used by my fuzzer is limited. If all non-malware XLS files on VARTotals can be used for corups distillation, the coverage result will be better and there will be more output. Acknowledgement. Special thanks to Jacques Kapper's blogs, the topics he shared at POC 2020 conference, his open source Pentagon project, and the XLS seed files he generously shared, all of which helped me a lot. And special thanks to Hick Yao Zhihua. Some of his fun ideas have inspired me a lot. Thank you for your attention. Thank you.